Welcome everybody on Zoom. Welcome everybody in the lecture hall. So this week, we are going to continue on document stores with MongoDB. Okay, I'll start right ahead with a question that will keep you busy. So, here you go. How does a document store the documents physically? You can take your clicker up and try to answer this question. This is something that we've covered last week, so normally you should already know the answer to this question. Okay, let's start looking at your answers. We have a majority, which is BSON, an optimized binary format. And the majority is correct that indeed MongoDB stores the document as BSON. What is BSON? It's a binary version of JSON. The fact that we can store things in a binary format is not new. This is something I mentioned before, right? So for example, if you have valid JSON, you can store it as Parquet together with a schema, and this is highly compact. Now, BSON is not like Parquet. BSON is not like Parquet because in BSON, you don't have a schema. It's still, I would call it a mess in the sense that you can have plenty of objects that have nothing to do with each other, but it's still more compact than text because there's a way you can optimize instead of all the curly braces. You have a single byte that says now comes an object and so on and so on. So this is a binary format. It doesn't only support JSON in the sense of string, number, Boolean, null, object arrays. It also has a few more types like dates, and so on, right? So it's a bit of an extended version of the JSON data model that is stored in a binary format. The fact that we have other types than string, number, Boolean, null is actually not new, right? In the data model week, we saw that when you validate, you can actually create way more types than just the ones you have in the JSON syntax, right? We'll know more, we'll see more when it comes to JSONic and querying. All right. Now, the text files could be done in that way on the local disk, but it would be less efficient to read because you need to parse them every time, right? On top of HDFS, no, simply because MongoDB is not running on HDFS, right? It's just running on the local drives that you have on your machines. So it's not like HBase, for example, that would be on HDFS. The last answer is incorrect because of MongoDB, but it's generally not incorrect in the sense that it would be a valid implementation of a document store. Because if you think in terms of data independence, that's exactly the idea, right? You can implement it in any way you want. In fact, of course, I mean that as a joke, but if you go back in time and go a few thousand years ago, this is pretty much what people were doing in libraries, right? They were, putting books on shelves and so on. So you could consider that a document store in the antiquity, right? Like a book is a document and you organize them on the shelves, you index them. So in a way, a library could be seen as some sort of document store in a fancy way. All right, so now let's get back to the slides. I need to load back. There you go. Oh, what? Okay, something's happening that is not good. It might be the light. I put more light. Yeah, what I will do is just switch off the shared screen. In the sense, how do I stop share? the first time that it does that. So I will just stop share there. Where is the, oh, it's there. Yeah, stop share. Then I think I just need to select the green somewhere, that I need to take some backgrounds. Then I take, hopefully, then come back. Then we share the screens. And now I'm going to cross my fingers. Okay, now that's good. So I'll start with a reminder of what we've already seen on document stores. The one thing to understand, which is actually not just specific to document stores, is that a data set is often a huge collection of small things. In that case, huge means thousands, millions, billions, trillions. Small things typically means not more than 16 megabytes. In many systems, the number might vary, but megabyte is typically the scale at which you have things, right? So it's a huge collection of rather small documents. These documents might contain nested structures like arrays, but for example, you're not going to find arrays with a billion members, right? That doesn't exist. The billion and trillion, that's really on the top level for the size of the collection, right? So just to, again, clarify that. The second thing that I insisted on last time is that there are two kinds of systems. There are the systems that are based on some proprietary and hidden storage, like PostgreSQL, relational databases are typically like that. MongoDB is like that. It means that you as a user don't know and don't care about the hard drive and what is stored on the hard drive. You just put data in there with the API of the system. You import the data. It's called ETLing the data, extract, transform, load. You have scripts for that. You can bring some JSON, and then you use the scripts in order to have MongoDB import it, right? And then MongoDB is going to store that as BSON, but you don't even care about BSON. You don't ever see any BSON, right? It's just hidden on the drive. On the other hand, you have in situ querying, which is based on data lakes, where you have a system like cloud storage, HDFS, and so on, and you just drop your data in there. On a data lake, you just put your data set as files there, and then you query them in situ, which is Latin for where they are, right? So Spark is an example of that. When you use Python and Pandas, it's kind of also that on the local drive, you can read your data. Hadoop MapReduce is the same. HBase, that depends how you look at it. HBase, you have two ways of looking at it. Either you consider that HBase is the logical layer on top of HDFS, then that would be an ETL system, because to put things in HBase, you have to use the HBase API. But other people view HBase as a storage system, meaning that they actually use it to store XML and JSON documents in HBase. So in that case, they actually view HBase as a data lake. So you can either view HBase as a data lake in that way, that you use it as a storage that efficiently stores and looks up and scans data, or you can see it as a logical layer on top of HDFS, which requires importing. For whom is that clear, that there is a blurry zone for HBase? Okay, awesome. Okay, then we looked at these CRUD things, create, read, update, delete, which is a paradigm that is much simpler than a full-fledged relational database management system, right? Where you have selection, projection, and so on. This is a bit lightweight, create, read, update, delete. In fact, it's not really unlike object storage and key value stores, right? Or even HBase, like you can put something, can get something, can delete something. So it's a pretty simple API. And that's pretty much what MongoDB is. In that sense, this is one of the reasons why MongoDB cannot really be compared directly with PostgreSQL, because MongoDB would not have the equivalence of a language like SQL. It wouldn't have the equivalence of a nicely encapsulated relational algebra. So you should consider that MongoDB is on a slightly lower level in terms of abstraction. In fact, this is why we don't often call it a database system. We usually say data store rather than database system. By the way, a reminder that PostgreSDB is not a database. It's a database management system. The database, that's the data itself, right? Just to clarify in the terminology. Okay, then we looked at the API, and I insist on API. It's not a query language. It's an API that is actually hosted in an imperative language, which in that case is JavaScript. And then the API has plenty of documentation explaining how that works, but we saw that in fine, the first parameter is a selection, which is some JSON objects. You cannot really play guessing games there because it's really made based on design decisions, and very often you just need to look up on the documentation the details, because that's really what the engineers decided. The second parameter is the projection, where you have the fields that you can project to using one, right? So this is what we saw last time, and I put a SQL cheat sheet that is basically the equivalent thing in SQL whenever that makes sense. And again, the selection is done with a where clause and the projection with the select clause. Okay, then I told you about the dollars that are special keywords in MongoDB. In that case, you ask for publications greater than or equal to 100, and you get the first and third documents in there. I also told you that the order actually goes across types. You can even compare integers and strings and binaries and arrays and objects and so on. But the way it's done is really trivial, in the sense that there is an arbitrary ordering across type that says every string is always smaller than every number, which is every smaller than every array, which is always smaller than every object. So it's more like a lexicographic order with first the type and then the value within the type. For whom is that clear? Right. This is for heterogeneity. So if you have data that is a huge mess and you can have multiple types with the same field, then this is how it's handled without an error. Okay. Then again, another side on heterogeneity, you could have missing fields, right? So here you look for theory relativity, and you might have some objects that miss it, like the last one at the bottom doesn't have any theory relativity, so it's not returned. And here you might have theory, which is something else, right? It's a different type. And then again, we saw this ordering, so this is obviously not the same, right? False is a Boolean that is not the same as relativity, but you don't get an error. In that case, it just doesn't return the documents. Okay, you can test for null. What is important is that in MongoDB, they made the decision that null is the same as the absence of value, as far as I know, so they don't make any difference. So if you ask for null, you basically ask for the absence of a field. This is not true of all systems. There are other systems that distinguish between null or an absent value. It's not the same. So it would be more generic to not distinguish, but to distinguish, but some systems don't. Okay. So in that case, you say theory null, which has the semantics not of looking for null, but of looking for absent theory keys, right? That's the last one. Okay, now here's a trivia. What does this return, name.first? So you might think several things. Maybe you might think, okay, the dot is not special in any way, so it's just looking for objects that have a key that is exactly called name.first, and that is associated with Albert. Another thing you might think of is this, and you would be correct that it's a lookup, it's a navigation. So the dot, just like the dollar, the dot is special, the period. So if you have name.first, you really look for first within an object that is associated with name, right? So the dot is special, it's not just any character. So in that case, you return the first and the second one because it matches the value Albert, right? For whom is that clear? So beware, the dollar is special, the dot is special. You might have thought, if you didn't know about the dot, of doing something like that, maybe thinking that this is going to just detect a pattern in which you have first Albert, maybe with other keys, but first Albert within name. That wouldn't work, because in that case, you might expect that it returns this, but it doesn't. Because in fact, it's a full comparison of the entire object, which is not the same as that entire object, because here there are two keys, here there is one key. That's called also a deep equal comparison, right? So they are not deep equal, these two objects. This here is deep equal. First Albert, it's exactly the same thing. So beware, if you don't use the dot, but you use this nested object, it's an exact match, deep equal. But if you use the dots, then there can be other keys in there, okay? And something that I think one of you asked last time, but I can also repeat it, is that when you query for an atomic value, a string, a number or something, it is actually also going to return arrays that contain that value, right? So if you look for theory, special relativity, it's also going to return documents that have an array containing special relativity. Now, this is what I meant with you cannot guess these things. It's really a decision that the engineering team of MongoDB made. That's it. You need to look at the documentation, and this is how it is. Maybe other products would do it differently, but there is no specific theory that tells you this is how it has to be, right? So this is just a design decision of MongoDB. It's quite convenient, actually, because you can easily find documents like this. Okay. There's other operators like $in that allows you to locate values within a list of values. Or do we have questions? Yes, there is a question over there. Oops, short.
So is the dot character just the same thing as the in operator, or is there a difference?
The dot, this one here?
Yeah.
Is it the same as?
The in operator.
Oh, the in operator. Not exactly. So the in operator is basically the same one as the same one as you have in SQL. It's basically like an or, saying university in ETH Zurich EPFL is logically equivalent to saying university is ETH Zurich or university is EPFL, right? That's what $in would mean here. Does it answer your question?
Thank you.
Awesome. Yeah. So you also have $not in, which is the opposite, which means that it's in none of these values, right? Remember, maybe I didn't explain, but some of you might know in SQL, you can also do that, right? You can also have a where clause with a colon in, and then you can nest another select from where that returns a list of values to find it in, right? Okay. Okay, so I think we've pretty much looked on the high level on the find function, right? That does a selection and projection. Now, there's plenty of keywords. There are many, many more than those I showed you. It's a whole list of keywords that is documented in MongoDB. And now some particularities, but there's many, many other particularities there, right? By the way, I think the way most people interact with MongoDB is they don't actually look up the documentation directly. I also don't. I think it's because it's not easy to find stuff just by opening the documentation and looking for it with the navigation. So what people do is they just type it in a search engine of their liking, and then they type their query with MongoDB, and then it's going to just return links to the MongoDB documentation, right? That's the easiest way that you find what you're looking for with MongoDB. Okay. On exam day, you won't have to program in MongoDB. You might have theoretical questions or queries on your screen, but you won't have to actually write queries in MongoDB. It's not going to be installed on the machine. Okay, let's look at other functions besides finds. This is a count function. You can call it after finds. So it's like JavaScript is object-oriented, right? So find returns the results in some wrapped in some JavaScript object. Then you do .count, and it returns the total number of values or items in your query, right? This should be clear what count does, right? Then you have sort, which is like the order by in SQL. Now, of course, this is again some design that -1 means decreasing and 1 means increasing. This is also arbitrary. That's the decision of the API, right? You can specify multiple keys. And here, that's also, where it teaches me, right? As after I told you that JSON, the keys are not ordered in an object and so on. In that case, they are actually ordered, meaning that MongoDB does care the order in which you give the sorting keys, right? It's going to first sort by the first one, then the second one, then the third one, right? So it's a bit of a breach of the semantics of JSON, but basically it's just going to consider the order in which you put them, okay? Then you have skip and limits, which is basically the limit and offset of SQL. So this is something that you also are familiar with from before. As a reminder, offset didn't exist in Spark SQL, but here it exists, offset, right? That's just the skip is basically the offset, just called differently. So here you skip the first 30 and then you return the next step, okay? Something important that can confuse people is that this is just an API. So in fact, I could swap the order of skip, limit, sort. I could write them in any order. It would still return the same results. So you should not read this as a chain of function calls like object-oriented. Rather, you should see it as some sort of API where you specify that you're going to skip 30, that you're going to sort by founded, and you're going to limit to 10. But the specification can be in any order, right? That's something that some people might find counterintuitive, right? Okay, then there is distinct that basically asks how many values are there for the key last in the collection. And there is a fancy function called aggregate that's called an aggregation pipeline. where you take a collection and then you have a pipeline of things that you do, right? You match century 20, then you group by year and count by sum, then you sort by count -1, then you limit by 5. Sounds very fancy, looks very fancy, looks very verbose, looks complex, but in fact, I'm pretty sure that this is familiar territory for you. Who recognizes a pattern here on that slide? Who is in familiar territory here, even without knowing MongoDB? So what do you recognize here? Anybody wants to share? Anybody wants to say what you recognize? Yes?
If I'm not mistaken, it does look similar to SQL, right? Because we actually...
Yes, that is correct. Yeah, it does look like SQL because you could interpret that as a select, where century is 20, group by year, and then in the projection, you have the count and the year. Then you have order by, counts descending, and then limit 5. You're absolutely correct. It looks like SQL. You could implement SQL in that way. Is there something else that this reminds you of? The fact that you have a series of, things that you do. Yes, go ahead.
Spark.
Yes, exactly. That resembles Spark. You see, there's everything in there. There's the creation with the collection. There is the action that aggregates. There is a transformation, 4 transformations, and there's all the stages in there. So this is just like MapReduce and Spark, really. So that's why I'm not going to teach you that. You can just read the documentation of that, and you would figure it out quite easily because that's the same. Yes?
Just a quick question on what was mentioned related to the necessity of having the things that we pass for sort in actual order, that like the order that we want them to be sorted as. I was wondering, could it actually be more valid if this was instead an array?
Yes.
Why maybe that's not the case, or is it like...
There was a meeting with the engineering team. Maybe they drank a lot of orange juice. No, I'm just joking. It might be that in other languages it's different. I think in Python, I vaguely remember that in Python it might be an array, but I'm not entirely sure. You can look that up. It would be more correct if I had to do it. I mean, if I wanted to do an API, because as you will see, I prefer query languages, but if you wanted to do an API, probably an array would be more correct. Yes, because the array has an order according to the semantics. An object normally doesn't.
Thank you.
I can say a few more words about the order in objects. So there is also something to consider that is not a semantic thing, but it's just a convenience thing. You will notice that in many systems that support JSON and that support JSON objects, although the order doesn't matter, it will still preserve the insertion order, meaning that the order that you provide when you put the data in the system, when you look it up again, the order will be the same. It doesn't have to be. It would also be correct to shuffle things within an object, would still be the same value logically, but it doesn't. The reason it doesn't is not that it's semantically meaningful. The reason it doesn't is just that it surprises people less. Right? It's just convenience to just recognize the order that you see in there. But the problem is that it's a double-edged sword, because the minute you start actually returning it in the same order, that very moment, some people start abusing it in this way. They start relying on the order and say, okay, now that I rely on the order, there is an order. And then you basically broke the contract of JSON that says the objects are normally unordered. That's actually something you're familiar as computer scientists, right? When you use a piece of software, and then you rely on semantics that is undocumented at your own risk, right? Normally, you should really check that the documentation specifies the features that you actually rely on, because then at the next release, it might actually break because the undocumented things actually changed. Okay, did I answer your question?
There's some question.
Yes, over there. Yes, go ahead.
What is happening with quote marks?
What is, sorry?
Quote marks, are they, because I mean, if you're talking about JavaScript, they're not really the same, right? I mean, the first sort and limit are not quote marks, but the sum is quote mark.
Oh, the quotes. Yep, very good question, I get it. This is also an abuse of JSON. You will find many systems that will not complain if you drop the quotes. Here, the idea is this. if you produce JSON, always put the quotes. If you produce JSON, that way you know that everybody will be able to read it. If you parse JSON, then it's nice to be lenient, because that way, even if people forgot the quotes, you can still parse it. It's kind of a tolerance thing, right? You just extend your system to also allow without quotes. In MongoDB, they are actually lenient on the quotes, so they will not actually complain. They will just silently add them back, right? It still has the semantic of a string. It's just that it's being nice to you. I actually think for pedagogical reasons, I should add back the quotes. That would be pedagogically more meaningful. As far as I remember, with the MongoDB documentation, they changed in some releases. I think they used to have quotes everywhere, then they dropped them in the documented examples. So that might change depending on the versions. But again, pedagogically, if you want to do things right, just put quotes everywhere. Then you're safe.
But it is JavaScript, it doesn't really matter, right?
It might, oh yes, that's a good point. It might be JavaScript also. Yeah, I'm less of a specialist. It might be that JavaScript allows, and that's the reason, because JavaScript allows without quotes, then it will work. Yeah. Yep, that's a good point too. It's actually from JavaScript. Okay, any other questions? Yes, over there. Maybe you can throw the catch box to your colleague on the right. Yeah.
So in the grouping line, like how should we interpret that line?
You should interpret that as a group by year, and then in the select you have year and sum of count as count.
Ah, okay.
Right. That would be pretty much what it does. Really, I just have one slide on that because this is really something I'm basically, what I want to say here is with what I've taught you on Spark and MapReduce, now you can go ahead and learn anything very rapidly that is similar. This is similar. That's why I'm not going to teach it, right? It would be very easy for you to figure that all out. Okay, then you have functions to insert. You can insert one object at a time or many at a time with insert many. You can update many objects at a time, like in that case, you update all of those that have last equal Einstein, then you set the century to 20. There's also an update one that exists, and then there is delete many, delete one. So delete many, deletes all that have the century equals to 15, for example. So you have insert, update, delete, and that's intuitive. I think you probably all understand what these do, and for the details, you can look up the spec. Now, what happens if 100 people are connected to the same MongoDB collection, which can happen? It's behind the website. Well, the granularity is one document. You never have two people modifying the same document at the same time, right? The collection, yes, you can have multiple people working on the same collection, but the document is locked for the duration of the query. You're guaranteed that nobody else is going to touch the same document as you do, right? So there is really a round robin on the documents for every document, okay? This is less than what you find in SQL systems, because in SQL system with ACID, you can actually block the entire database with transactions, right? But here it's just one document. Now, there exist query languages on top of document stores and data lakes with JSON. That's just a few of them. We might start today or tomorrow using JSONic. A query language is different from an API because then you don't have JavaScript or Java or any host language anymore. It's just like SQL. You directly type your query. Yes, go ahead. There is a question over there.
Regarding the locking of the resources, is that a limitation of scaling for MongoDB or not?
I think it evolves over time. I remember last time I used it, but that was a while ago. People just had a couple of machines, like 4 or 5 machines. I will also explain a little bit how it works. I think that probably they made a bit of progress and you scale more. I actually don't know how people pushed it today, if they actually managed to build larger clusters. Last time I checked, it didn't have the scalability that you get with HDFS or with HBase in terms of quantity, right? Some people use MongoDB on just one machine and they're just fine with that. Right? Did I answer your question? Okay. Now, the architecture. So that's good that you actually pointed to that. So the same principles as everywhere else. We shard the data. If it's across machines, we partition the collections. We replicate the data. We're going to store several times the partition. And we buy lots of cheap hardware. just maybe not as much as HDFS or HBase. And the way it works is that we replicate the entire collection several times, but we also partition it. So you see these 2 dimensions. In 1 dimension, we replicate vertically and we partition horizontally. So the way that it works here is that all the replicas of a specific partition, that's called a replica set. More exactly, what's actually called a replica set is the hardware that stores that partition several times. So it's a bit differently from what you've seen before, right? So here you have this centralized architecture, but this is for every replica set you have that. So you have the primary node in there and secondary nodes, but just 2 of them. Typically, you can have 3. It's just not going to be a large scale. And that's just, there's a replica on every machine. So in that case, you would have 3 replicates of the partitions that are stored here. You have one replica here, one replica here, one replica there, right? And it's this machine that handles the connection. This is just for replication. Okay, and then you have several replica sets. So this is when you start sharding, right? And you distribute over multiple replica sets. In that case, it's as if you would have 3 data nodes in HDFS. But again, this is very different from HDFS because in HDFS, you remember that the replicas are spread all over the data nodes. Here you have very strict boundaries between the replica sets. So it's really a different architecture. So every shard here is going to contain specific partitions of the collection, and it's going to store it both on the primary and on the secondaries, right? Here you see that shard, it's used sometimes for data. It's a shard of data. Here it's more of a shard like the hardware that stores the shards, right? Okay. So what happens now when you write? So here that's a replica set that has 5 secondaries instead of just 2. If you write something to MongoDB, do we have a question? Yes.
If you go back to the previous slide, so then each specific shard will use a different set of machines, or could it be that they actually share? So for example, maybe the primary in the second one is actually a secondary from another replica set, or how does that work?
I think these are separate machines,
So
right? At least virtually.
So in this case, we would have 9 machines.
Yep.
Okay.
Yep, exactly.
I was wondering how efficient that is to just use them, because if a shard is, for example,
that's exactly why the way people use MongoDB, they will typically not have so many machines, right? They will really buy a couple of machines, but then a machine is used entirely, for a secondary within a shard or a primary within a shard. Typically, you fill them before you buy new machines. You start filling the existing ones.
I suppose then in general there aren't that many shards then, but actually sharding is not done as much. If you just have 1 or 2 machines, then you would just keep everything on those 2 machines. You only have 1 shard.
Well, if you have 2 machines, you probably want to have a primary and a secondary of a single replica set. It's probably not a good idea to have 2 primaries, because if you lose data, yeah, that's probably a bit risky. You can do it, of course, if you want. Some people use just 1 primary and that's it. But
thank you.
Thank you. Yes, go ahead.
I have 2 questions. So what is the scale of MongoDB? Like the order, at least tens, hundreds, how many machines?
I should check for the latest, but I think the last time I saw that it was a couple of terabytes. I don't know if now people pushed it to petabytes, but now, since somebody asked as well, we should put it on our agenda to double check if we find any information on how people pushed it so far.
My second question is what happens when the database is queried? Like, who receives the query? How is it forwarded to the right shard, the right
Yep.
How the right piece of data is found?
So there are processes running on these machines, and then there is a general process that receives the queries, and then that process is going to communicate with all the shards, more precisely the primaries of the shards, right? And then it's basically, if you run a filtering query, for example, it's just going to subdivide it into filtering sub-queries on every replica set.
So the primaries form like the ring from the distributed hash tables and like communicating with one another and know.
Yes, you could think of it that way, but the difference is that the hashing is done in intervals and not with hashes. So it's not like you hash like you do in a hash table. Here you shard by saying A to F, G to M, and so on. So what you do is actually you build an index. I will show you how, and then based on an index, you can ask to partition according to a key that is indexed, right? So it's integrated with the index, right?
Thank you.
Okay. So now a few words on when you write. What happens is that when you write, it's going to write on the primary, then it propagates, but you don't have to wait for everything. You don't have to wait for confirmation from everybody. For example, you can say, I just need 3 confirmations and that's it. And 3, that's it. And then it's just going to continue propagating in the background to the others, right? You can specify that as a user. That's called the write concern, right? You can say 1 if you don't care. You can say the maximum number of machines if you really, really don't want to lose anything. Okay. Okay, now I'm going to go to indices. Indices are actually more general than just document stores. That's also a good brush up because they are similar to relational database systems. And the idea is that you can create indices on your data. That's something you cannot do on data lakes, right? You can do it because this is a storage of its own that is optimized, and so it also supports indices. Indices are for fast retrieval. For example, imagine that you want to easily find the foods that have a specific color. How do you index that in such a way that it's fast, right? So this is what we want to do here. So we can have very big collections like this. We know with, here's an example with 2 rows. And for example, somebody might want to find a specific person. This is called the point query, right? Because they all have unique names, and you find name Euler, it just returns one document. So this is called the point query in benchmarks. Then there are queries that might have a filtering criteria that is more permissive. For example, if you filter by profession, maybe you're going to have hundreds of them, right? Then it's no longer a point query. It's just not highly filtering, you could call it, right? Just returns plenty of objects, right? So these are the sort of things that you benchmark. This normally should be super, super fast, a point query. This might be a bit less fast, but still, if it's still a small part of the entire collection, you can improve with an index. You also have queries that are called ranged queries, which try to retrieve a range of values from a specific attribute. For example, here, everybody with a year after 1900s, right? So this is a range query. Okay. So the question is, how can we make these queries super fast? And we do this by indexing stuff. So an index is a structure, a little bit like what is here, that basically lists all the values you want to use for your query. So here you index by color, and every color points to the documents that have it. For example, yellow points to banana and ananas, right? So this is the idea. Now you imagine if you take a color, it's super fast to retrieve the documents that have that color. But there is a price to pay. It's that somebody had to go through the trouble of creating that index. In that case, it was me. In the case of MongoDB, it's going to be the MongoDB engine that will create that structure for you. But I have to show you how these structures actually look like. So I'd start with hash indices, which are the fastest. So a hash index computes the hash of every value and puts it in a hash table, right? So I assume many of you know hash tables as computer scientists. So you can just say create index on the column century as a hash, and that will make queries on century very fast, the lookups on century. What it does is that it creates a hash table like this, with a column for the actual value and then the records. A hash index works with this magic function that's called the hash function, h, that is deterministic, even though it uses some pseudo-randomness with the seed and so on, but basically it always returns the same value once you have picked your seed. Then you say h of 20 returns 0, so that's position 0 in the array, you put it there and you add a pointer. Then 21 might, oh, I think that was just a mistake that I forgot to update this one, should be 21. Let's move to the 19, I'll fix that. So imagine h of 19 is 4, so that puts it in the 4th position, so 5th if you start counting with 0, plus the pointer. Then -4 gives you 3, so it's there, -6 gives you 1, so it's there, and 20, it's again there, right? So the idea is that now that you've done that, you can, at query time, look at the query. It looks for century 19. So you take h of 19, which again is deterministic. So you're going to get exactly the same hash as you got when you built the index. So that's 4. And then you know that an array lookup is O of 1, exactly. O of 1, so that's very fast. H is also very fast to compute, just a bunch of addition, multiplication, and modulo stuff. And then you follow pointers in memory, so it's all O of 1, right? So this is O of 1, this. Amazing. Imagine without an index, you have 1 trillion object, you need to scan the entire collection, can take hours. With an index, you actually get O of 1, okay? But there's issues with that. So first, hash indices take space because you need maybe a sparse table if you want to avoid collisions, because that actually is more costly. If you have collisions, then you need to add lists within the cells. So you have space requirements, and range queries cannot work like that. It's exactly like the key value stores, actually. If you have a range, there's no way you can figure out a range here because the hash just distributes the values all over the place, so it doesn't preserve the intervals. There is no way you can execute a range query. So we need another index structure for that, and these are B plus trees. B plus trees are index structures that support range queries. So it looks like that. A B plus tree is basically optimized for disk access in the sense that you know that when you access a disk, you access in blocks, right? 4 kilobytes. We already discussed that roughly. And so we try to have the leaves in there the size of a disk block for efficient retrieval. On my slides, I just put 3 values in every leaf, but of course, in reality, it's going to be more than that. Okay, so that's just the reason. And then there's a few constraints for B plus trees. First, all the leaves are exactly at the same depth, always. In that case, it's depth 2. Second, you have some interval, that's a parameter of the B plus tree that specifies how many children you can have at every non-leaf node. So for example, here you say it's between 3 and 5, can be 3, can be 4, can be 5. More generally, it's D plus 1 to D plus 1. And you choose what D you want, right? What value of D. That gives you a specification. But there is an exception. The root is the only node that is allowed to have less than D plus 1. In that case, less than 3, it has 2, and that's fine, right? That's the only exception. Every other node has to have between 3 and 5 children. Now, in a B plus tree, the actual values that you index on are at the leaves. So at the leaves, you're going to have all of the values that appear in your collection. You built it that way. So these are all, in that case, the values that appeared in the collection. The values right here, they are only for the lookup purposes, right? So you typically use the same ones, right? You just take the leftmost value from the leaf, you just reuse it there, right? So this is just for comparison. Everything that's smaller lexicographically than possess is on the left, everything that's bigger is on the right, and then that's just like a binary search kind of structure, right? Well, not just binary in that case, but you just go down looking for your intervals. For whom is that clear? Okay, so this is called the B plus tree, right? Now, a word of warning, when you say between 3 and 5 children, that actually means between 2 and 4 values. That's an interval thing, right? If you have entries, then you have n minus 1 intervals, right? That's just something to be careful about, because even though it's easy to understand, people tend to forget it, right? So if I say between 3 and 5 children, then to compare on these 3 children, that would be 2 keys, and for 5 children, that would be 4 keys, right? For whom is that clear? Imagine that I have 2 keys. Then I can be smaller than the first key, I can be between the 2 keys, or I can be on the right of the other key. That's 3 possibilities, 3 children for 2 keys. Okay, so this is what is meant here, right? So you have 3 children means 2 keys. And this constraint on between 3 and 5 children, which is between 2 and 4 keys, also applies to the leaves. So if you say between 3 and 5 children, then the leaves must have between 2 and 4 keys, right? Okay, now I have an animation before we take a break. If I insert stuff in there, then 1, 2, 3, I just insert, and maybe I want it to not allow more than 4. If I have between 3 and 5 children, that would be 6 children, right? Virtually, it's a leaf, so it doesn't have the children, but that would be 6. So we don't like that. What do? We split. There you go. I add 1 level. Now I have a new root that has only 2 children, but that's fine, it's the root. And now I have 3 values on the left and 2 on the right. So it's between 2 and 4 values, so we are good. Then I add 6, I add 7, I add 8. It's just for the example, I have increasing integers, of course, but it doesn't have to be. Now we are back to the problem that we have too many values here. So we have to split. So we pick the one in the middle, 7, and there you go. We add a 7 in the root. So now the root has 3 children, 9, 10, 11, we have the problem again. So we just split again. Then the root has 4 children. That's still fine. Then we continue adding. So here I took a shortcut that I went all the way to 16. Now I add 17. Oh, that's too much. So I split. But now that's too much on the root. And there goes yet another level, right? I split the root. And this is how you grow the B plus tree. Make no mistake, this is very, very, very tough to implement, right? If I ask you to implement one, that would really take a while. This is why we are not actually going to implement any. It's very, very challenging to implement and to get right. Yes? What is the? Oh, to implement or to look up? To implement, I think it's probably at least a few days to get it right. Oh, to look up, you mean? So not the implementation itself.
I mean,
to look up, yeah. So it's logarithmic, right? Because it's like, intuitively, it's like a binary search, right? So intuitively, if you start at the root, the number of comparisons you are going to do is logarithmic in the total number of nodes at the leaves, right? Does it make sense? Logarithmic. So this is different from the hash index, which is O of 1. Here it's O of log n, which is still better than O of n, right? The scan would be O of n. But if you have this index, it's O of log n, which is actually quite good, right? Yes, just checking the time because I also owe you a break, which it's already 1:03. So you will ask your question first after the break. And then, yeah, so you've deserved your break. See you in 15 minutes for the continuation of the lecture. Thank you.